Quantum computing. The dawn of a new era. Introduction. In an era where technology evolves at an unprecedented pace, quantum computing stands as one of the most promising frontiers. With roots tracing back to the early 1980s, this groundbreaking discipline draws on the principles of quantum mechanics that govern atomic and subatomic processes. Unlike classical computers, which employ bits as the smallest unit of data, quantum computers utilize qubits, enabling them to perform complex calculations at staggering speeds. What lies ahead is not merely an innovation but a paradigm shift, capable of redefining fields ranging from cryptography to materials science. The quantum leap, a quantum primer. To understand quantum computing, one must first grasp the fundamental principles of quantum mechanics. Classical bits represent information as either 0 or 1, serving as the building blocks of computer processing. In contrast, qubits can exist in multiple states simultaneously, thanks to the phenomenon known as superposition. This feature allows quantum computers to perform numerous calculations at once, exponentially increasing their potential processing power. Another essential principle is entanglement, a peculiar connection that allows qubits to be interconnected regardless of distance. When qubits are entangled, changing the state of one qubit instantaneously affects the other, laying the groundwork for unprecedented computational capabilities. Historical context and evolution. The journey of quantum computing began with physicists like Richard Feynman and David Deutsch, who posited that classical computers would struggle to simulate quantum systems. However, the field remained largely theoretical until the 1990s, when breakthroughs such as Peter Shor's algorithm unveiled how quantum computers could factor large numbers exponentially faster than classical ones. This revelation sent shockwaves through the fields of cryptography and security, as it implied that many encryption methods would become obsolete. The advent of quantum computing not only sparked a flurry of research and investment but also ignited a competitive race among nations and corporations to harness this transformational technology. The architecture of quantum machines. Building a quantum computer involves a complex architecture distinct from classical machines. At the core are qubits, which can be realized through various physical implementations, including trapped ions, superconducting circuits, and topological qubits. Each approach carries its unique set of advantages and challenges. For instance, superconducting qubits, pioneered by companies like IBM and Google, leverage superconducting materials to create qubits that can represent and manipulate quantum states. Conversely, trapped ion qubits utilize electromagnetic fields to hold ions in place, facilitating high-precision operations. Regardless of the approach, the overarching challenge remains maintaining qubit coherence amidst the pervasive noise of their environments. Quantum algorithms, a new kind of logic. Quantum computing's true utility arises from its sophisticated algorithms. Among the most notable is Shor's algorithm, which can factor integers in polynomial time, a feat that poses a threat to widely used public key cryptography. For large integers, classical algorithms take exponentially longer, making Shor's algorithm a game-changer in cybersecurity. Another groundbreaking algorithm is Grover's search algorithm, which can theoretically search through unsorted databases quadratically faster than classical counterparts. These algorithms showcase the potential of quantum computing to solve problems once thought intractable and present a new toolkit to address challenges in complex optimization, machine learning, and drug discovery. The quantum computing ecosystem. As quantum computing evolves, an extensive ecosystem of stakeholders has emerged. Industry leaders like IBM, Google, Microsoft, and startups such as Rigetti and IonQ are making significant strides. These companies are investing heavily in research, development, and talent acquisition to maintain their competitive edge. Additionally, academic institutions like MIT and Stanford are nurturing the next generation of quantum engineers and computer scientists. Moreover, government agencies worldwide are launching initiatives to advance quantum research, recognizing its potential economic and strategic significance. Each player contributes to a collaborative ecosystem, pooling resources and expertise to accelerate progress. The challenge of quantum decoherence. One of the primary hurdles in quantum computing is decoherence, the loss of quantum coherence due to environmental interactions. Decoherence can cause qubits to lose their entangled states, thereby crippling the computational advantages that quantum computing promises. Engineers and researchers are devising error correction codes and fault-tolerant quantum computing techniques to mitigate decoherence effects. These strategies often require the redundancy of qubits, increasing the complexity of quantum systems. Nevertheless, overcoming these obstacles is crucial for building practical and scalable quantum computers that can operate in real-world conditions. Potential applications. Beyond imagination. The ramifications of quantum computing extend well beyond traditional computing tasks. In pharmaceuticals, quantum computers can simulate molecular interactions at unprecedented speeds, facilitating drug discovery and personalized medicine. In finance, they could optimize trading strategies and minimize risks by analyzing vast datasets in real time. Supply chain optimization and logistics also stand to benefit, as quantum algorithms can tackle complex models involving numerous variables and constraints. Additionally, quantum computing offers new paradigms in artificial intelligence, where its processing speed could lead to breakthroughs in deep learning and data analytics. Quantum cryptography, security at a new level. As quantum computers threaten conventional encryption methods, quantum cryptography emerges as a beacon of hope. Quantum key distribution, QKD, utilizes the principles of quantum mechanics to create a secure communication channel. In QKD, any attempt to eavesdrop on the quantum key alters its state, alerting the parties involved. This feature ensures the integrity and confidentiality of information, making quantum cryptography a valuable asset for secure communications in both government and private sectors. The ability to guarantee secure data transmission in a post-quantum world highlights the dual role of quantum technology. It serves as both a threat and a solution. Quantum supremacy, a milestone achieved. In 2019, Google announced it had achieved quantum supremacy and a milestone, indicating that quantum computers could solve problems that classical computers could not, or could do so much more quickly. The experiment involved a complex calculation completed in approximately 200 seconds on a quantum processor, while the most advanced classical supercomputers would have taken thousands of years to accomplish the same task. This moment was a watershed in the quest for practical quantum computing, though it also sparked debates regarding the implications and realism of such claims. While achieving quantum supremacy, the emphasis was placed not on practical applications, but rather on the potential future value of quantum technologies. Bridging the gap. Quantum cloud computing. Recognizing the need for accessibility, companies are increasingly offering quantum computing as a cloud service. This approach democratizes access to quantum technology, enabling researchers and developers around the world to experiment with quantum algorithms without needing to own a quantum computer. Platforms like IBM's Quantum Experience and Amazon's Breakit provide users with environments to test and run quantum-related tasks. These services foster innovation and collaboration, as different players can build and refine algorithms, contributing to the collective advancement of the field while allowing smaller companies and academic institutions to participate meaningfully. Education and talent development. As quantum computing evolves, it creates a parallel imperative for education and talent development. Universities and online platforms are developing curricula to equip students with the skills necessary to thrive in the quantum era. Courses ranging from quantum mechanics to quantum programming are being tailored for the next generation of scientists and engineers. Companies, too, are investing in upskilling their workforce to adapt to quantum paradigms. In this context, education becomes a purposeful bridge to the quantum future, ensuring that the workforce is prepared to exploit the promise of this groundbreaking technology. Ethical and societal implications. However, as with any powerful technology, quantum computing raises ethical and societal questions. The security implications of quantum computing on privacy and personal data are profound. If quantum computing can easily break existing encryption methods, individuals and organizations could face unprecedented risks concerning data theft and breaches of privacy. Furthermore, the potential for this technology to create an uneven playing field in industries such as finance and healthcare raises questions of equity and transparency. Addressing these ethical dilemmas will be crucial as society navigates the transformative potential of quantum technology. A global race for quantum leadership. The race to lead in quantum computing is not confined to the private sector. It is a global initiative involving governments vying for technological supremacy. The United States, China, and the European Union are among the nations investing heavily in quantum technology initiatives, driven by the belief that quantum advancements could yield significant strategic advantages. These investments encompass not only research and development but also public-private partnerships aimed at bridging the gap between theoretical research and practical applications. This global race underscores the significance of quantum technology on the world stage, making it a vital component of national policies and international collaborations. The future, towards quantum integration. As quantum computing continues its evolution, the prospect of integrating quantum and classical systems will become increasingly vital. The ability to harvest the strengths of both paradigms could enable a wide variety of applications that leverage the computational speed of quantum machines with the stability of classical computing. Hybrid approaches would allow industries to optimally address problems that require not only speed but also reliability. This integration could also foster the development of new software architectures capable of executing quantum algorithms seamlessly within existing frameworks. Conclusion. Quantum computing is not merely a technological curiosity. It represents the dawn of a new era characterized by profound implications for science, industry, and society at large. As researchers break barriers, developing practical solutions to exponential growth in computational power and new algorithms, the landscape will continuously shift from redefining fields like cryptography and pharmaceuticals to initiating a spiraling evolution in artificial intelligence. The significance of quantum computing will only intensify. The narrative surrounding this emerging field is not just about understanding quantum principles but also about preparing for a future shaped by such innovations, creating policies and systems that embrace the technology, while safeguarding social values. The ongoing journey, rife with challenges and opportunities, promises to redefine what we know about computation and its role in our world.